In this video, I'd like to explain the purpose of writing a data analysis plan. Let us start by an example. A recent study described the results of an experiment. 29 different data analysis teams were asked to address exactly the same research question, and that this research question was whether or not referees were more likely to give a red card in soccer to players with a dark toned skin compared to players with a light toned skin. And it would not be surprised that each of these 29 teams came up with their own approach. In other words, there are many different ways that lead to Rome. Here we see that there were initially 32 data analysis teams, but only 29 analysis teams presented some results. And we can see that none of the covariables that were accessible to the data analysis teams were used by all of them. Most of the teams used the variable position in 62% of the times, but for example, the referee variable was used markedly less, just 7%. Also, the final effect measure differed between the teams. Most of the teams reported an odds ratio larger than 1, which indicated that indeed referees were more likely to give a red card to a player with a dark toned skin compared to a player with a white toned skin. But the size of the odds ratio differed between the teams, and also the confidence interval differed markedly between the teams. Now, what does that have to do with an analysis plan? Well, analysis plan is actually nothing more than thinking about a strategy before you do your data analysis. It is a strategy that leads up to the presentation of your final results. So why would we make such an analysis plan? Well, it is to keep you on the right track, to give you directions where to go with your data analysis. Don't forget that most likely you will get a large database with a large number of variables, and you need some guidance how to move to your final product. But also it prevents you from taking the wrong turn. It is very well described that researchers are consciously or unconsciously prone to interpreting results the way that they wish they could be interpreted, or even that they draw up their hypothesis or the research questions after they have already analyzed the data. And this might lead again to very selective reporting of the results, only those that are deemed statistically significant. So what is in general described in a data analysis plan? It needs to refer to the research question that you have at hand, and that might be one question or multiple questions. And it must be made clear which populations are there in your study. Are there specific inclusion criteria, exclusion criteria, and how are you going to implement these criteria in your data analysis? Which variables do you choose for your data analysis? As said, often you have a choice of a large number of variables, but to make statistical models efficient, you have to make selections of these. What rules are you going to use to select these variables? And how are you going to deal with missing data? Every data set will have missing data, and you need to define a strategy upfront how to deal with these. Which models are you going to use to derive at your effect measures? It is always good to have this clear vision about your models right from the start, and that stops you from trying different methods leading to different results, and just pick those methods that fits your results best. Analysis plans also have a section on dummy tables and dummy graphs. That is actually a way how you think that you are going to present your results, and by doing this it gives you a very good way of organizing and analyzing your data. Now let us look at those issues in a little bit more detail. To start with the research questions. It is obvious that this question needs to be precise. So for example, if I have a question like what is the role of computer-aided diagnosis in chest X-ray, I have a research question that is not giving me much information. One type of computer-aided diagnosis, CAD, is often used in tuberculosis, where chest X-rays from suspected patients can be read by an algorithm that then identifies areas in the lungs that are abnormal. So my first position might already be that I indicate that I'm dealing with tuberculosis. So does CAD contribute to the diagnosis of tuberculosis? But there are many forms of tuberculosis. Which diagnosis am I looking for? Well, maybe we can rephrase it as does the use of CAD reduce the frequency of clinical TB? Here I'm clearly more specific about which type of tuberculosis I'm talking about, and also I add a measure of frequency. But in which patients am I looking? Here I add that at least I'm looking at TB patients that present in the outpatient clinic in 2021, even with a clear time frame, because outpatients are completely different than inpatients with tuberculosis. And if I have a clear time frame, it would be wise to also have a comparison for that time frame. So my final research question, although not perfect yet, can be does the use of CAD reduce the frequency of clinical TB in patients visiting the outpatient department in 2021 compared to 2020? So the studied population tells me who can join the study, or at least who can join the analysis, because sometimes or often the analysis done is on a subgroup of the patients who were there in the study. And it would be wise to specifically mention whether there are children, pregnant women or vulnerable populations in your study population. And why is that? Because it is a really balance between practical versus ethical. As soon as you have research done on children or pregnant women or specific vulnerable populations, then a lot of ethical issues come into play. Of course, ethical issues other than the normal ethical issues that are referring to any scientific project. Leaving those groups out makes research much more practical, but raises the questions whether or not the results in the end will be generalizable. And which data set am I going to use? Which time frame are my data going to have, and what are the source of my data? And here we're talking more about completeness versus representativeness. We know that disease registers are easy to come by. You can have large time frames for these data, but we also know that disease registers are not always complete, let alone that they are representative. Instead, I can do a very representative study with adequate sampling strategies, but the time frame to do that might be much smaller. Data analysis is never done in a vacuum. Data analysis assumes that there is some theoretical framework that indicate how variables work together. So let us again talk about an example. What if my research question was about association between social isolation and dementia, with the hypothesis that if there is more social isolation, an individual would have earlier or more severe dementia? You can think of that social isolation has to do something with family structures in which that person is living. But is the effect of family a direct effect on dementia, which could be possible if there are some genetic factors at play? Or is family much more related to the environment where that person is living? An environment maybe where there is a lot of smoking. And is smoking then not related to dementia? And if so, is that directly, or does it go through alcohol use, which we know is strongly associated with smoking? Or is smoking having an effect on atherosclerosis? And we know that atherosclerosis is one of the possible causes of dementia. So only with a few variables in that example, there can already be very complex structures how these variables work together. And in your data analysis plan, you describe these complex structures. You describe how you assume that these variables work together. Because in one assumption it might be a mediator, in another assumption it might be a confounder. And you have to deal with mediators differently than with confounders. And then missing data. As said, almost always there will be missing data in your dataset. And how do you deal with this? A common way of dealing with it is to completely ignore it, but clearly this is not a good scientific practice. There are scientific domains where missing data are simply filled in through a median or a mean value or a last observation carried forward. Within the field of epidemiology and public health, missing data are much more approached by modeling the missing data through statistical models to fill in the blanks. Whichever way you're going to approach missing data, it needs to be described in your data analysis plan. And then dummy tables and dummy graphs. This is an example of a dummy table that I made for the analysis of a randomized clinical trial I was involved in. I knew right from the start that I had to report results for 2 different compounds and each compound having 2 different dosages. And I also knew that I had to report those outcomes for different time frames and time periods. And given the small number of participants in the study, I knew that I was going for a median and an interquartile range as the summary statistics. So by drawing this blank table in advance, it really guides me how I have to organize my data and which analysis I need to perform to be able to fill in this table. The same thing holds with a dummy graph, and this is one of the dummy graphs I made for another study where I had to describe an analysis using interrupted time series. And for that I needed to explain in the analysis plan how I was going to deal with shifting regressions during the follow-up. I envisioned 6 possibilities how my data would develop over time, and by drawing these graphs I could complement them with 6 underlying statistical formulas that could capture these developments over time. Now once you have drawn up an analysis plan, can you divert from it? Yes, you can. You can divert from the analysis plan, and often you have to. You cannot think of every potential problem right from the start. But be aware, for many studies you have to register that study, including the data analysis plan, in an open access repository. And by the time of your publications, reviewers will compare your initial data analysis plan with the results that you are presenting in your final manuscript. And that is to see whether or not you diverted from the analysis plan. And as I said, it's not a problem to divert, but then you have to give arguments why you diverted. And this is all to maintain the idea that you did not manipulate the data or manipulate analysis to find the answers that you wished that were there. So the key points for a data analysis plan is that you draft this plan a priori, probably before your data collection, but at least before data analysis, before seeing the data. Such a plan guides data management and data analysis, and by doing so prevents you from conscious or unconscious manipulation. And of course, conscious manipulation is more or less synonymous with scientific fraud. But it also improves reproducibility of your research, especially when you post your data analysis plan on an open access repository. Other researchers can really see what you wanted to do and what you have done and compare that with the final results. And as said, this is increasingly mandatory for publication your final manuscript.